Well, dear, welcome back. So, we are discussing today modeling technique of robot, and isn't it great that some designer has given you a physical robot structure, and you are modeling using simple um, linear algebra, that is modeling in a matrix form, and computer can understand it, so that computer can understand it, and then you can, of course, program. Okay, and as you know, the very common data structure is there for inputting matrix. So our basic aim is to make robot model using linear algebra so that computer can understand. Okay, and step by step we are going towards that, and this is already we have deduced in my earlier class that any serial kinematic chain between two successive link, the transformation matrix, 4 by 4 transformation matrix, can be deduced in this form. Okay, and what is there in this form? In this form, and this is essentially we have used de Novet Hartenberg notation. Okay, great idea, right? In this form, you are having everything which is possible between two successive link. You have captured link length, you have captured link twist, you have captured motion parameter. Okay, so and you have also captured the deviation between the two successive joint. Okay, now just recap. Whenever you could figure out the joint, you assign your z coordinate frame. Okay, and then between two distance between the minimum distance between two successive z coordinate is your common normal. Okay, a. So, and then the motion parameter is theta. You have assigned if it is a revolute type of joint, and then distance between two successive common normal, which is denoting the offset, the way the physical structure has been built. If there is offset, offset could be 0, but assume it is there, so it will be the distance between two successive common normal. Okay, and then if the link is twisted, one end is twisted to the other end, then that is measured. That is the angle between two successive z axis, and it is measured in the yz plane about x axis. That's all you have, right, in de Novet Hartenberg notation. Okay, and using all this, di is the distance between two successive common normal, ai is the common normal, theta is the motion parameter, right, and alpha is the twist angle. So everything is captured in this 4 cross 4 matrix. Now this is a mother matrix we will use for modeling any kind of robot. So let us first take a 2-link planar manipulator robot, simplest. Okay, so this is our 2-link, and let us assume that xy is the coordinate frame which is fixed, which is ground coordinate frame, we are calling 0th coordinate frame, and link 1, the body coordinate frame of the link 1 is say 1, coordinate frame 1. So and link 2 coordinate body coordinate frame is frame 2, and at this end we have assigned a tool coordinate frame. Okay, and this is actually, you see, a little bit over constrained. Why? Because the manipulator can only reach to a point. It cannot pose its gripper. Why? Because only two, as I have drawn here, only 2 link is there, theta 1 and theta 2. But as you know, any physical body, if it is placed on a plane, how many degrees of freedom it has? 3, right? X, Y, and motion about Z. So 3 degrees of freedom. To capture 3 degrees of freedom, I need 3 degrees of freedom robot. But here, well, I will not call it robot. This manipulator has only 2 degrees of freedom. But nevertheless, I am just taking a small example to show you how it works. We'll take more general, realistic robot example. So the moment some designer has given you this robot, two-link robot, you assign this coordinate frame. And what is the rule? That is a very fundamental rule, common sense rule. So you have a zeroth coordinate frame, which is fixed. And initially, and this link is moving, right? This is just like my hand, okay? It's moving like this, okay? And at any instant, let us assume that first coordinate frame and zeroth coordinate frame are completely overlapped. Why I am doing that? Because that will make sure when I will prepare the DH table, most of the parameter will be 0. So that's the reason. And then similar is the case for tool coordinate frame. Okay, here it is not visible, but it will be visible elsewhere. Similarly, frame number 2 you assigned to link 2 at the joint. This is second joint, but attached to the link 2, because this is the body coordinate frame of link 2. So this is about coordinate frame attachment, and attach a coordinate frame T, tool coordinate frame we call, here at the middle of the gripper. Okay. Now, first thing you will have to do after coordinate frame attachment, what you will have to do? You will have to prepare a DH table, Dinavet Hartenberg table. Okay. How many columns will be there in the table? 1, 2, 3, 4, 5. In every robot, there will be 5 columns. Okay. So this is say link, denoting link number I, okay, and here say I am putting twist angle alpha I minus 1, because also you know that between two coordinate frame I and I minus 1, the two parameters, that is twist angle and common normal, is measured with the help of I minus 1 coordinate frame with respect to I minus 1 coordinate frame, whereas di and theta I are measured with reference to ith coordinate frame. That's why notation is very scientific, you know. So these notations are actually as per your textbook, which is Introduction to Robotics by Craig, John J. Craig, and I have several copies in the library, so you won't have any problem, and you can even have one copy, okay. But it's a very fundamental book, and the notations are as part of that book, so that it will inspire you to read. Even you are not reading, you concentrate here. So the twist angle and the distance between two successive, this is a common normal, right? So alpha I minus 1, this is common normal AI minus 1. Di is the distance between two successive common normal, and theta I is the motion parameter. Okay. Well, both theta and di could be motion parameter. If it is a revolute type of joint, that is signature is RRR, here RR, then this will be the variable. Okay, this will move when the robot is moving. Whereas if I have a robot where with prismatic joint, PP type robot, then di will be varying. So you see, out of all these 4 parameters, in case of robot, only one at a time will vary. Okay, if it is a revolute type of robot, then the moment the designer has given you this robot, okay, so this is fixed, twist angle is fixed because design you cannot change, the AI minus 1 is fixed, di is fixed, so that's why they are called geometrical parameter. If it is a revolute joint robot, they are geometrical parameter. Okay? So they will never change with the motion of the robot, and this is motion parameter. So for revolute joint. For prismatic joint, so these and theta, they will be geometric parameter and di will be motion parameter. Well, so first you prepare DH table and then you see you have assigned coordinate frame here, some geometry is given, that what is the link length is that, and then you fill up the form, you fill up the table. Link 1 and link 0, initially I told that they were overlapped. So what will be the alpha? Alpha is between two z-axis and they are overlapping, so it is 0. What is I minus 1? That is the common normal. Is the distance between two successive z-axis, and where the z-axis are overlapping, it will be 0. What is di? Di is the distance between two successive common normal. The question doesn't arise here to have any when common normal is not there. Okay, so it is also 0. So what is remaining? Theta 1. But theta 1 is not constant. At a particular instant I have drawn this table. Theta 1 is a function of time. So with motion it will vary. Got it? So first for link 1, all the row is filled up. Okay. Now 2, link 2, that means, and you see, what are the z-axis? Z-axis are perpendicular, this is planar manipulator, right? Perpendicular to the plane of the board. Here the computer monitor, perpendicular to the plane. Okay. So here is frame 2. So what is alpha? That is twist angle. You see, the z is perpendicular to the plane of the board. This z is perpendicular to the plane of the board, and two z are parallel. If two joint axes are parallel, is there any twist? No, twist angle is 0. Okay, so it is 0. And then what is the common normal, length of the common normal? Length of the common normal is the minimum distance between two z-axis. And here, when two z-axis are parallel, you can have innumerable, you can take any one, that is your link length. Here it is L1, okay, given, so L1 is link length. And what is the distance between two successive common normal? Here again, there is no, only one common normal I have. Unless we have another common normal, we cannot have the distance between them. So it is again 0. And then again theta 2 is a variable. So these are actually function of time, please remember. They are not constant, not fixed. With motion, kinematically, when I am drawing this particular position, they are theta 1, theta 2 fixed, but they are not actually fixed. Okay, so that's it. Now you see, there's another link. I wanted to show you why I have told coordinate frame, what is the significance, although here is no degrees of freedom attached, right? It is, I should say, it is over constrained. Okay, so I should have been here another degrees of freedom, because 3 degrees of freedom I need to capture a pose. Like if a body is like this gripper cannot grip it like that. Okay, it will never be able to do that. Okay, because of the structure, but it will be able to move to the position. Okay, xy. So now number 3. So what is there is no z-axis because motion is not taking place. So the alpha is 0. Then the distance between two successive z-axis, you can fictitiously assume that z-axis is there, but it is not rotating. It's a passive z-axis, which is perpendicular to the plane of the board again. So this is perpendicular to the plane. This is perpendicular to the board. This is perpendicular to the board. All are perpendicular to the board. So this is L2. And what is the distance between two successive common normal? Is there any offset? No, because you see parallel. This is parallel, right? Z-axis. So offset, there is no offset, 0. And Is there any motion parameter here? Is a passive link? As I told you, motion parameter is 0. Well, so this is very, very important, very, very critical. These two, step 1 and step 2, is the most critical one, and as an engineer, you need to be very perfect in doing this. If you make any mistake, then the mistake will be propagated. So once you have prepared this, then you see what I am doing. I am reading a particular row, putting the values here. So I equals to 1. Then what is I minus 1? 0. That means I am getting a transformation matrix 1 with respect to 0. And what is that matrix? I will use this mother matrix and put all the values, this row values here. First, here theta 1, so theta 1 minus sine theta 2. Then 0. What is A? A is 0, so it is 0. Second row, cos alpha 0 means 1, so only sine theta 1 remains. Cos theta 2, so this is again sine theta 1, sine theta 2, cos theta 1, 0, 0. Same. Here I am putting these values. Okay. Now third row again sine theta 1. Okay. Sine alpha is 0. That's why it becomes 0. Okay. And then this is 0. This becomes cos 0 is 1, 0, 0, 0, 0, 1. So merely this is remaining. Isn't it great? Means you know that it is a particular case only when you are rotating about z-axis by an angle theta 1. Okay. So this is a general one. They may lead to many particular matrix. So this is one matrix done. Now read row number 2 and put I equals to 2. So now I need to get homogeneous coordinate transformation matrix 2 link 2 with respect to link 1. 2 minus 1 is 1. And then use the same matrix with these row values. Okay. So now cos theta 2 minus sin theta 2, 0. And now ai minus 1 is L1. So L1 is here. So then this is again sine 0 is 0. Sine 0 is, so 0, 0. Then this is twist angle is 0. So that's why it is 1. Cos 0 is 1. And then di into this one. And di is actually 0. So this is 0. So you see, it's a kind of sparse matrix. Many things are 0. This is very good thing. And this is happening, many are 0 because you have judiciously placed 0 and 1. You see, I could have put somewhere here 0th coordinate frame, and then one coordinate frame is here, another coordinate frame is here. This would have been very bad idea, right? That will not make my matrix 0. Why I want this kind of matrix? I want to capture only motion parameter, and sparse matrix is good. As many zeros are there, computation will be less. Well, now concentrate on the third row. So transformation matrix of link 3 with respect to 2, you see, because this is a passive joint, no motion, so this is the rotation part of the matrix is a unitary matrix, okay, and this I created only to capture L2, okay, so here everything, this is a unitary matrix, and all L2 will be there only, that is the distance between two z-axis. This is a z-axis perpendicular to the plane of the board. This is another z-axis, and the distance between them is L2. So L2 remains here. Well, so these are the three matrix we already have. Once you have, then you have everything. What is that everything? Now, 3 with respect to 0. How you will get it? Just repeatedly doing that. So we just multiply these matrices. This is a function of theta 1. This is a matrix function of theta 2. This is, well, theta 3. There is no theta 3 because this is not a function of theta 3. But if had it been theta 3, means thrilling manipulator, then this would have been. So this is a constant only, okay, here. And that's what you have got. So one good thing, again I am repeating, that each matrix in robotics, although there are 4 parameters, there will be only and only one variable rotation parameter. Function means theta 1 is only variable, theta 2 is only variable. That's good, okay? And now, again I am repeating in a matrix form, if this 4 by 4 matrix is given and I require to figure out theta 1, theta 2, it is inverse kinematic solution. But if I plug in some theta 1, theta 2 value and compute this 3 multiplication, which I will do, and as a result of that, whatever you will get is the final destination of the fingertip of the robot, okay? So now let us do the modeling, same, okay? So what you can see, I'm quickly drawing I'm repeating almost, so that now you will do with me x, y. So this is my 0th coordinate frame, and this is my first coordinate frame, and this is my second coordinate frame. This is perpendicular though. Okay, and this is my tool coordinate frame. Okay, so alpha I minus 1 a I minus 1 di theta I. You see, this is the mother matrix. We have deduced it. Whenever you develop model for any robot, you need this matrix. Okay, 0, 0, 0, theta 1. Okay, 0, L1, 0, theta 2, 0, L2, 0, 0. So this is what exactly this matrix is. Now you have, so you can do one thing. So forward kinematics, inverse kinematics is clearly understood now. Now I am putting the basic matrix which I have got last page. Okay, quickly. So this was cos theta 1 minus sin theta 1, then 0, 0, sin theta 1, cos theta 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So side by side I need to write because I will have to multiply them. Okay, cos theta 2 minus sin theta 2, 0, L1. Okay, I am putting the boundary so that I will write everything within this. Okay, cos theta 2. See, very, very simple, repetitive in nature. those who are scared about seeing those matrices. So I am doing this so that you will fill now friendship 1 0 0 2 with such kind of oops, this is 1 0 0 0 1. So these are the three matrices you have. Okay, so now just you multiply. Now I am going to write this is equals to R11, R12, R13, Px, R21, R22, R23 into Py, R31, R32, R33 into Pz 0 0 0 1. Okay, so this is what this matrix is. Okay, I am writing. Now you just multiply them. Okay, very quickly. Cos theta 2 keep it as it is, minus sin theta 1 0 0 sin theta 1 cos theta 1 0 0 0 0 1 0 0 0 0 1. And now again matrix multiplication 12 class. If I make mistake, you correct this multiplied by this. Okay, so this is becoming your cos theta 2 minus sin theta 2 0. You see, this is cos theta 1 only remains, this is minus sin theta 1 remains, this is gone, so this is 0, and this is L2 cos theta 2, right? This multiplied by this, and this multiplied by this multiplied by this, and this multiplied by this. So what are remaining? Cos theta 2 into L2. Oops, I write it down. L2 cos theta 2 plus L1. This is that element. Okay. So first row, fourth column element is this. Then quickly same thing, you'll have to multiply cos theta 2 0 L2 sin theta 2. So 0 0 1 0 0 0 0 1. Great. So this multiplication has been done. Okay, this and this resulted this. Now I need to multiply this to get the final. Okay, so you will get, so I am writing C means cos theta. Okay, cos theta 1 plus theta 2. You see, cos theta 1 into cos theta 2. So you will have to now multiply this, right? Cos theta 1, cos theta 2 minus sin theta 1, sin theta 2, that is equals to cos theta 1 plus theta 2. So I wrote like this. 12 class arithmetic, trigonometry, minus sin theta 1 plus theta 2, 0. And then this one L2 cos theta 1 plus theta 2 plus L1 cos theta 1. This is the first row. Second row will be sin theta 1 plus theta 2 cos theta 1 plus theta 2 0 and L2 sin theta 1 plus theta 2 plus L1 sin theta 1. 0 1 0 1 0 0 0 1. So that's it. So this is the manipulator we call manipulator model. Okay. Now see, I have R11, R12, R13, Px, R21, R22, R23, Py, R31, R32, R33, Pz, 0, 0, 0, 1. Isn't it very simple? Huh? So this is completely this manipulator. Okay, let us give it a manipulator shape. Okay. Huh? Just like my hand type of manipulator. Okay. Its model is this. So now you can make program. What is that? You can, if this is now, of course, if this is given, this you will get. Simply you put the values and you will get 4 by 4 matrix, and all R11, R12, everything will be known. This is called forward kinematics. But when I will give this, what is this? This is called pose, which is a combination of position plus orientation. Position and orientation is called pose. Now, if the pose is given, means all the elements are given, then you need to figure out what is theta 1 and theta 2 is called inverse kinematic solution. And how do I do that? You see, very simple. In the simple case, here, this will generate how many equations? 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16 equation you will generate. But out of them, this is giving nothing to you. This is trivial. Okay, so no use. So now, this will be equal to this. This equal to this will give another equation. This equal to this will give another equation. Okay. Similarly, I will just make a point here because this is of my interest. This, when equated with the corresponding elements, so this is matrix, no? Linear algebra, a little bit. So left hand side matrix, right hand side matrix, each element has to be equal. So I can generate, these are not giving me, see, this will, unknown is, this can also give you something, right? Unknown is theta 1 and theta 2. Okay. So I can just write Px equals to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Or Py equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So this is exactly, if somebody take the help of 12th class math and try to figure out only for tooling manipulator. So this is XY point at any instant of time. Say this is theta 1, and this is the angle theta 2, which is made by the second link. So this is link 1, this is link length L2. So second link is making with respect to first link. So this is parallel. So what is this angle? Theta 1 plus theta 2. So if I just project, what is x? X coordinate? X coordinate is this projection, that is this, plus extend it a little bit, this. So what is this? This is nothing but L1 cos theta 1. You see L1 cos theta 1. And what is this one? This is the link length is L2. So L2 cos theta 1 plus theta 2, because theta 2 is the angle made with first link. So theta 1 and theta 2 is the angle made with the x-axis. This simple geometry, okay? So what you are getting with a simple geometry, with projection, simple projection, with DH principle, with all matrix, I wanted to say that similarly, okay, you just project, let me complete in this direction. So L1 sin theta 1, and projection will be, so y will be equals to, y coordinate will be equal to L1 sin theta 1, that is projection on y-axis, projection of this link on y-axis, okay, or extended y-axis will give you this equation. So in this way you are getting this, in this using DH principle, using such and such matrix, you are getting the same thing, just to show you that whatever you have done is correct. But remember, this will fail, okay? And I will show you, this will not work. Simple thing will not work when there will be real robot having several degrees of freedom, having different structure, but this will prevail, okay? That's why it is very important to know this way to develop the model of a robot manipulator. And we will continue, we will take several examples of now real robot, slowly real robot. I will take you up to the Puma robot, and I will use the same tiny, elegant Dinovet-Hartenberg principle to develop model of those robots. And those models will be useful for solving inverse kinematics, forward kinematics, trajectory planning, dynamics, every kind of thing. The model which you are developing will be extremely useful. So it is very, very important that you understand the DH principle, which is extremely simple, okay? And next class I will try to tell you that how to assign, maybe here 5 minutes I have, okay? So how to assign coordinate frame now, you need to know. So wherever you see, say these are my two link, okay? So wherever you will see the joint axis, you put your z axis, okay? This is ith link z axis, this I minus 1 link z axis, and the distance between these two z axes, wherever you see, okay, if they are not parallel or intersecting, then there will be a common normal. And what will be that? The common normal will be both perpendicular to this axis as well as to this axis, and assign x-axis there. So x-axis is towards the direction of common normal, z-axis is towards the direction of motion axis. Link after link you do that, okay? And you see here, so where to put the origin, wherever you see that it is meeting, that will be the origin of the I minus 1 coordinate frame. Where to I coordinate frame origin? Here. Why? Because there is another link whose common normal is this, which is meeting I coordinate frame here. So, okay, that you will have to understand. And the distance between two successive common normal is actually di, that is link offset, you can think. And motion parameters are about z-axis, okay? And pictorially I am just trying to show you. And how much twist of this end with respect to that end, how to measure? measurement is what is the angle between two successive z axes. How to know that? So I'll have to project this z axis with this axis perpendicular to the plane. What plane? YZ plane. You see why I am not writing here, okay, because that will make your figure clumsy, but it is defined. The moment you have Z and X, Y cannot have any other thing. So you can assume that this, you see, projection, this Z axis has been projected here. That is why this is parallel, okay? And this is the angle, alpha I minus 1 is a twist angle. So motion parameter, twist angle, distance in the common normal, distance between two common normal di and the common normal. These are the four base parameter which completely describe links when they are connected. With this, I will continue from here in the next class because this is the most important part of robot model. Okay, we can call it robot anatomy, and I'll continue from here. But till then, stay safe and try to digest. Now you need to I will solve many problems. You need to solve many problems so that everything will be crystal clear. Okay, have a nice day. Bye bye.